I hope you guys enjoyed the review. If you would take out your optional practice test and turn to number 5, I would like to go over a couple problems with you utilizing the information that we've learned over the past few days. So number 5 says that we have 2 liters of hydrogen chloride gas being dissolved in water, creating a solution with a total volume of 550 milliliters. And we're asked to answer some questions about that solution. Now, hydrogen chloride, when it dissolves in water, will become hydrochloric acid, whereas that when 2 liters is dissolved to create a solution with 550 milliliters of volume, what is the molarity of the solution? Well, remember that molarity is moles of solute per liter of solution. So if we know moles of hydrogen chloride or hydrochloric acid and we know the total volume of the solution, we can find the molarity of the solution. So we have 2 liters of a gas being dissolved, and we know that at STP, 1 mole of any gas is 22.4 liters. So we can use that to convert liters of HCl to moles of HCl. So if we take 2.00 liters of HCl and convert that to moles, 22.4 liters of HCl is 1 mole of HCl. This gives 0.089285743 moles of HCl. So now that we have moles, we can take moles and divide it by the volume in liters to find molarity. So we take moles and then divide it by 0.55000 liters. That's just the volume in milliliters converted to liters. And I get the molarity of the solution with significant figures to be 0.162 molar. So we have a hydrochloric acid solution that is 0.162 molar. Now moving on to B, it says, what is the hydronium ion concentration? Now remember, hydronium ion is really the same thing as hydrogen ion. So we're looking for the hydrogen ion concentration. Now we need to think about what our solute is if we have a strong acid, a weak acid, a strong base, or a weak base in order to answer this question and the following questions. Our acid in this particular example is hydrochloric, which is a strong acid. So knowing that I have a strong acid, I know that the hydrogen ion concentration for any strong acid solution is equal to the concentration of the acid, in this case hydrochloric acid. So I know that my hydrogen ion concentration must be 0.162 molar as well. So now onto the hydroxide ion concentration. Well, we learned that the hydrogen ion concentration and the hydroxide ion concentration are related. If we take the hydrogen ion times the hydroxide ion concentration, we should get 1 times 10 to the minus 14th. And this value is Kw, which is the ion product constant for water. So we know that we have the hydrogen ion concentration here, so we can plug that in here. So 0.162 molar times the hydroxide ion concentration is equal to 1 times 10 to the minus 14th. So solving for the hydroxide ion concentration, I divide both sides by 0.162 molar. Divide this side by the same. And I calculate the hydroxide ion concentration to be with significant figures, 6.17 times 10 to the minus 14th molar. Next, we have, what is the pH? Well, we learned that the pH is related to the hydrogen ion concentration, and we can find it by taking the negative log of the hydrogen ion concentration. So if I plug in the hydrogen ion concentration from above, I'm going to take the negative log of 0.162. And when I calculate this, I get the pH to be 0.790. Now remember, there's a quirky thing with sig figs when we're dealing with concentrations in pH or pOH. The total sig figs in the concentration, so the total number of sig figs here, which is 3 sig figs, should equal the number of decimal places that I have in my pH or pOH values. So I have 3 decimal places here since there are 3 sig figs in the concentration value. And then lastly, what is the pOH? Now there's 2 ways we could approach finding this, and either is going to give us the same answer. We could either take the negative log, pOH is the negative log of the hydroxide ion concentration, which we calculated above, or we could recognize that pH and pOH are related by this equation. And we can plug in the pH and solve for the pOH. And so in doing that, I calculated the pOH to be 13.209. So this problem was about recognizing that we had a solution of a strong acid, using that to identify the hydronium ion or the hydrogen ion concentration, and then using the hydrogen ion concentration to calculate the hydroxide ion concentration, and then using those 2 pieces of information to find the pH and the pOH. Let's go on to our next example. Our next example asks us to consider a 1.25 times 10 to the minus second molar solution of potassium hydroxide and to answer the following questions. Now looking at this, I see I have potassium hydroxide, which is a strong base. It's important that I recognize this as a strong base because that's going to help determine how I solve this problem. Now, when I think about answering part A, what is the hydronium ion concentration, I need some extra information to do that. What I can figure out quite easily is part B, what is the hydroxide ion concentration, because I know for a strong base, the hydroxide ion concentration is equal to the concentration of the base, so in this case, the concentration of the potassium hydroxide. So this question is as easy as me identifying that the potassium hydroxide solution is a 1.25 times 10 to the minus second molar solution, and saying then, okay, our hydroxide ion is the same. So 1.25 times 10 to the minus second molar. So that answers that question. Now that I have that piece of information, I know that the hydrogen ion concentration and the hydroxide ion concentration are related, so I can use that to solve part A. So the hydrogen ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the minus 14. So I can just plug this value in here and I can solve for the hydroxide ion concentration. So to do that, I take the hydrogen ion concentration times 1.25 times 10 to the minus second molar, and that's equal to 1 times 10 to the minus 14. To solve for the hydrogen ion concentration, I divide both sides by 1.25 times 10 to the minus second molar. And I calculate the hydrogen ion concentration to be 8.00 times 10 to the minus 13 molar. Now that I have both the hydrogen ion concentration calculated and the hydroxide ion concentration calculated, I can easily find the pH and the pOH. So looking at the pH, we know that the pH of a solution is equal to the negative log of the hydrogen ion concentration. So to calculate the pH of this solution, we take the negative log of and then plug in our hydrogen ion concentration, which is 8.00 times 10 to the minus 13th, and solve. And so when I solved that, I got the pH to be 12.097. Again, remember that quirky thing with sig figs, so we look at how many sig figs we have in our concentration values. So we see 3 sig figs in our concentration values, so that is then the number of decimal places that we should have in our pH and pOH values. Now we could take the negative log of the hydroxide ion concentration to find pOH, but I think it's a lot easier to recognize that pH plus pOH is equal to 14 and to solve for the pOH that way. So plugging this number in here for the pH, I calculate the pOH to be equal to 1.903. Okay, moving on to number 7. In this problem, we are looking at dissolving ammonia gas into water, creating a solution that has a total volume of 800 milliliters, and we're given information about the Kb for ammonia. Now, I want to point out that strong acids and strong bases do not have Ka or Kb values. So if you're given a Ka or a Kb value, that should be an automatic sign for you to recognize that that is a weak acid or a weak base. So here I see a Kb given for ammonia, so I'm immediately thinking weak base. So if I didn't already recognize ammonia as a weak base, that should indicate to me that I'm working with a weak base. So ammonia, NH3, it is not a compound that has hydroxide in it, so it is a weak base. But like I said, if you didn't recognize it as a weak base, the Kb should give that piece away. So I'm working with a weak base. It is important that you always identify if you have a strong acid, a weak acid, a strong base, or a weak base before you start solving these problems. So I'm working with a weak base, and I'm asked, what is the molarity of the solution? Well, we can find the molarity of this solution much like we found the molarity of the solution in number 5. We're given the volume of ammonia that we're dissolving into the solution. We can use that 1 mole at SCP is 22.4 liters to convert the volume in liters to moles, and then we can divide that by the total volume of the solution in liters. So molarity is equal to moles of solute per liter solution. So I'm going to take my 1.50 liters of ammonia and convert that to moles. So 22.4 liters of ammonia is equal to 1 mole of ammonia. And when I calculate that, I got 0.0669642857 moles ammonia. And that's in a total volume of 0.80000 liters. So when I calculate that to get the molarity, I get with sig figs 0.0837 molar. So my solution is a 0.0837 molar solution of ammonia. Now what is the hydronium ion concentration? Again, when I'm working with a base, starting with the hydronium ion concentration is not necessarily the best thing. I would prefer to think about the hydroxide ion concentration first, because we know that the hydroxide ion concentration for a base, for a weak base, is equal to the square root of the Kb, which we are given above, times the concentration of the base, which we have, excuse me, these should be brackets here, which we have just calculated. So we can plug in our numbers to this equation, find the hydroxide ion concentration, and then use that to find the hydrogen ion concentration. So in doing that, the hydroxide ion concentration is equal to the square root of 1.80 times 10 to the minus 5th times 0.0837 molar. And I calculated this to be 0.00122 molar. Now that I have the hydroxide ion concentration, I'm able to calculate the hydrogen or hydronium ion concentration. We know that the hydrogen ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the minus 14th. I'm assuming, since you've seen me solve this twice already in the two previous problems, that you're comfortable working that math. So in plugging in those numbers, we would calculate the hydrogen ion concentration to be 8.20 times 10 to the minus 12. I'm going to let you try that out yourself to make sure that you are coming up with the same number that I am. So plug in the hydroxide ion concentration here and solve for the hydrogen ion concentration. And you should come up with 8.20 times 10 to the minus 12 molar. Now that we have hydrogen ion concentration and the hydroxide ion concentration, finding pH and pOH is quite easy. We know the pH is equal to the negative log of the hydrogen ion concentration. So I can simply plug this in here. Again, I'm assuming, since you've seen me solve that twice now, that you can do that on your own. So when you calculate that by plugging in the 8.20 times 10 to the minus 12, you should calculate your pH to be 11.086. Remember significant figures? We have 3 significant figures in our concentrations, which means we should have 3 decimal places in our pH and pOH, so 11.086 is the answer that I get for the pH. The pH and pOH are related as follows. pH plus pOH is equal to 14. So I can then plug in the pH here and solve for the pOH. You could also take the negative log of the hydroxide ion concentration and come up with the same value. But regardless of which way you go about it, you should calculate the pOH to be 2.914. And then lastly, number 8, we have 1.5 moles of nitrous acid dissolved in water to create 2 liters of total solution. And we're given the Ka for nitrous acid. Again, when we're given a Ka or Kb, that automatically should indicate that we're working with something that's weak, in this case, an acid. Identifying that it is a weak acid is important in our problem solving, so it is really essential that that's one of the first things that you do when you're going to be solving one of these problems. Okay, so we have a weak acid, so we can find the hydrogen ion concentration by taking, we know for a weak acid the hydrogen ion concentration is the square root of the Ka times the concentration of the acid. In this case, it'll be of the nitrous acid. Oh, excuse me, that's nitric acid. So square root of the Ka times the concentration of the nitrous acid. Now we need to know the concentration of the nitrous acid to plug this in, so we have a little side calculating to do before we can actually plug in the values here. So what we will do is we will find the concentration of the nitrous acid solution by taking the 1.50 moles that are dissolved and dividing it by the 2 liters it's dissolved in. And this gives us a concentration of 0.75 molar HNO2. Now we can plug that value in here and find the hydrogen ion concentration, and then we can continue solving. What I'd like you to do is I would like you to fill out the form underneath this video. I would like you to indicate how well you feel you're understanding this material. I would like you to tell me any questions that you have so that I can address those with you on Monday. I would like you to then answer B, C, and D. So I'd like you to tell me the answers to B, C, and D. Now, when you're working with exponents, you can just use times 10 caret, and I will understand that you're implying that those are exponents if you need to show those in your answers. But please answer B, C, and D. This will help me understand whether you're understanding, and then I can help you guys on Monday accordingly. I hope you guys have a great weekend, and I hope you enjoyed this video, and I hope it will help you guys with your problem solving during this unit, and I hope you will enjoy the work time you'll get as a result of watching this video at home over the weekend. Thank you.